Atomic Structure, Lecture A. We're going to be talking about what makes up an atom. Atoms are the smallest part of any element, so they are the things that make up everything else around us. They're made of three parts. They call them subatomic particles because this prefix sub means below. Subatomic are parts that are smaller than an atom. Okay, so the three pieces we're responsible for: proton, electrons, and neutrons. When I shorthand them, I shorthand protons as a P with a little plus next to it because protons have a charge of +1. When I shorthand electrons, I shorthand them as an E with a little negative sign next to it because electrons have a charge of -1. And when I shorthand neutrons, I use a little N with an O next to it because neutrons are neutral and they have no charge at all. Take out your reference table and find reference table O. Reference table O is going to show you the symbols that they use for nuclear chemistry and the different ways that we write with them, the notations that we use. Okay, gamma radiation is not a particle, it's not matter, it's just energy. And it's energy that's released anytime we have something that's radioactive. So you'll notice it has 0, 0. The top number is the mass, and the bottom number is actually the charge. And a lot of times it also tells us the number of protons and helps us identify things, but it's the charge. So if you look at an alpha particle has a mass of 4 and a charge of +2. A beta particle, on the other hand, essentially has a mass of 0. Now it is a particle, so it has some mass, but it's really, really tiny, and we'll see what it is in your notes. And it has a charge of -1. Now they used to have in parentheses next to beta particle the word electron. A beta particle is an extremely fast electron. Beta particle, high-speed electron, same thing. So if you want to add that note to yourself, you can remember that. Here's the E that I use for my electron. There's the -1 for his charge. So no mass, charge -1. Neutrons that I was just talking about right here, mass of 1, charge of 0. And here's your proton, mass of 1, charge of +1. One of the things you're going to notice about a proton is a hydrogen nucleus. So he has a mass of 1 and a charge of +1, and they use the symbol H to represent it because he's made of 1 proton. And a hydrogen atom has a mass of 1 and an atomic number of 1. So he has 1 proton. And if this is an atom, he's going to have an electron configuration of 1. So he's going to have 1 electron. And when we subtract to get the neutrons, because that's how we find neutrons, mass minus atomic number, he has no neutrons. So when we take this electron away, he becomes a hydrogen with a +1 charge. That's just a proton. Positron's the only guy left down here, and he is antimatter. He is an equal but opposite beta particle. All right, back to our lecture notes. So atoms are made of protons, neutrons, and electrons. There are parts that are found compacted together in the center, and we call that center a nucleus. And unlike a cell that has a nuclear membrane, the nucleus of an atom is just going to be protons and neutrons kind of stuck together in the middle. It doesn't have anything that we can see that's holding it together. So it's just a force that holds it together. They call it strong nuclear forces. And these are the forces that we release when we split an atom in a nuclear reaction. That's the amount of energy that's given off during a nuclear explosion or in a nuclear power plant. It's this energy holding these guys together. Why does it take so much energy to hold them together? Well, what do we know about like charges? Like charges repel. You're trying to put a whole bunch of positive protons stuck together in the middle of your nucleus, and it's going to take some strong forces to hold them together. They think the neutrons are there to make that a little bit easier, but the neutrons have no charge. So the neutrons aren't holding the protons together. They're not doing anything other than kind of cushioning the protons one from the other. When we have atoms that have a 1-to-1 ratio of protons to neutrons, those are stable nuclei. When that proportion is not 1-to-1, then we tend to get things that are radioactive. Nucleons, if you look at this word, looks an awful lot like nucleus and neutron. You have to be really careful. If they say nucleons, they are referring to only protons and neutrons. Okay, so if they want to know what particles are in an atom, it's protons, electrons, and neutrons. If they want to know what the nucleons are, it's just protons and neutrons. All right, the nucleus always has a positive charge because it's made of things that are +1 and neutral. So the nucleus is always positive. They base the mass of these particles on one proton having a mass of 1 atomic mass unit. Neutrons are the same mass as protons. So neutrons and protons make up all of the mass of your atom. Okay, so that's the mass. So if we look at the atomic mass number, when we round them, so chlorine we've used an awful lot, and we round that to 35, the 35 is made of protons and neutrons. And the 17 is just protons. So if you want to find just neutrons, if we have just the protons and we have the protons and the neutrons, to find just the neutrons, we would subtract 35 minus 17 is going to be 18 neutrons in our chlorine. So the number of nucleons in chlorine is 35. The number of protons is 17. The number of neutrons is 18. If this chlorine is a neutral atom, he's going to have an equal number of electrons as protons because electrons are -1. So if there's 17 positive protons plus 17, we're going to need 17 negative electrons so that our total charge is 0. Electrons are found in regions called orbitals. Regions called orbitals. We will talk a lot about the orbitals, and we'll talk about orbital notation. And I will say this a whole bunch of times because one of the first questions on the final almost every single year has to do with where the electrons are found. And in the modern model, electrons are found in regions called orbitals, moving around the outside of the nucleus. So your nucleus is positive, and you have a cloud of electrons moving around the outside that's negative, so an atom is neutral. If they use the word atom, it is a neutral particle, and the number of protons is equal to the number of electrons. How do we know the structure of the atom when we can't look at an atom itself? So that has to do with experiments that other scientists did, mostly physicists. And one that they're going to ask you about is Ernest Rutherford's gold foil experiment. So Rutherford and gold foil, he had radioactive material. He knew it was shooting out alpha particles. So table O said alpha particles were these rather large, they're the largest of the subatomic particles, radioactive, it's spinning these things out, smaller than an atom. So Rutherford took gold because gold is the most malleable metal. So you can press gold foil out to the point where it's thinner than tissue paper, and had this phosphorescent screen around the outside. And the idea was where the radioactive particles would hit the screen, it would glow. And he was going to take measurements. He thought the particles would hit the gold, that it would either break the gold particles apart or they would bounce off. He had this film go all the way around his experiment. He was going to measure the angles that it came off. And what he found were that most of the alpha particles went straight through. And this was extremely shocking to him and everybody else because at the time they thought atoms were solid spheres. So he expected them to bounce off or to smash them into pieces. When most of them just went straight through with no resistance, some of them went through and angled a little bit and curved, but he said it was as if you took a tennis ball and threw it at a brick wall and it went straight through. That's how shocking it was. So what he concluded, since most of them went straight through, was that atoms are mostly empty space. They are mostly empty space. So we couldn't have this solid ball model of atoms anymore. We had to change it. Some of them bounced back, so he knew there was something hard in there, and that's where he had this idea of a dense nucleus. That they're mostly empty space, but there's a dense nucleus. You have a dense nucleus, and then you have these electrons zipping and moving around the outside, making it act like it's a solid sphere, but it's not. So our model of the atom has a dense nucleus where the protons and neutrons are found. That's where the mass is. It always has a positive charge. The positive charge is always going to be equal to the number of protons in its nucleus. The number of protons in its nucleus is his atomic number. The mass number is always a whole number. We're going to round that off, and it's protons and neutrons added together. If we want to find the number of neutrons, we subtract a mass number and atomic number. All right, moving on. You keep seeing that key with carbon-12, and we talk about the mass of carbon being 12, and carbon having 6 protons, 6 electrons, 6 neutrons. But you also heard carbon-14 a lot in earth science and biology because that's the one we use for radioactive dating, for carbon dating. Carbon-12 and carbon-14 are what we call isotopes. Isotopes are the same element. They're going to have the same atomic number, but they have different masses. So, in other words, there are different numbers of neutrons. So let's compare carbon-12 to carbon-14. So carbon-12 has a mass of 12 and an atomic number of 6. So I said the atomic number tells you the number of protons. If it's a neutral atom, the protons equal electrons. And to find the neutrons, we subtract. So 12 minus 6 is 6. If I have carbon-14, it's still carbon, so it still has to have 6 protons. Still carbon, still 6 protons. Still neutral, so it still has 6 electrons. But now 14 minus 6 is 8. It's heavier, it has 8 neutrons. Remember what I said earlier about the ratio of protons to neutrons? If it's 1 to 1, you have a pretty stable nucleus. The farther away from the 1 to 1 ratio you get, the more radioactive it is. So carbon-14 is a radioactive isotope of carbon-12. Iso means the same, so we're talking about the same element, but we're going to have different masses. So let's compare potassium-37 to potassium-42. Now, if I want to know how many protons, electrons, and neutrons there are, I need one more number. And that number is the atomic number, and we find that on our periodic table. So periodic table, we find potassium. Potassium is element 19. So I can put 19 in for my atomic number. The 19 I got from the periodic table. The farther this ratio gets from 1 to 1, the more unstable your nucleus is. Potassium-42 is going to be your radioactive isotope. Okay? All right. Reference table N lists some of our radioactive isotopes. And they show you their names both in symbols. So they're going to give you the atomic symbol and they put the mass. When they write the name and it's an isotope, they're going to write the name with a dash with the number after it. One of the things they like to do is ask you which pair would be isotopes, and what you're looking for is ones where the bottom number is the same and the top number is different. Those are isotopes. All right. Now, when you look at your periodic table, if we again go back to potassium, sorry to keep flipping, it says 39.0933. So it doesn't say exactly 39. Most of these don't. Magnesium 24.3 and sodium 22.9. They are decimals, but protons have a mass of 1 and neutrons have a mass of 1, and you can't have a quarter or a third or a half or a fraction of a proton or a neutron. So the mass numbers are always whole numbers. So why then on our periodic table do we have decimals for their mass unit? And that's because the atomic mass is a weighted average. It's a weighted average, and it's based on the percent of these isotopes that exist in nature. So we're going to practice doing weighted averages next. Okay, so when we look at weighted averages, we don't do it like a normal average. You're not going to just take two numbers and put them together and divide by 2. It doesn't work that way. It's going to be a weighted average. So we need to know what percent of the isotope there is in nature. So when we look at this example for copper, to try to explain what's going on, it says why is the atomic mass of copper 63.546 if copper has a mass number of 63. So most copper is 63, and in nature we have another isotope of copper, and we get about 30% of that isotope, and it's 65. So when they talk about fractional abundance, how much is there? Well, we have 30%, which is going to be like saying 0.3, which means how much copper 63 is there? Well, if 30% is 65 and they're telling us there's only these two isotopes, then 70% or 0.7 is going to be from copper 63. The mass of copper 63 is 63. So if we multiply 63 by 0.7, we get the weighted mass. So out of our mass, 44.1 AMUs would be from copper 63. If 30% is copper 65, to find the part or the percent that comes from copper 65. So if I want the total weighted average, I just add the two together. So 1 and 5 is 6, and 9 and 4 is 13. We carry the 1, 4, 5, 6, 63.6. So approximately what's on your table. So let's look at a couple of practice problems, and then we'll wrap this up for today. Okay, as a multiple choice question, when they talk about the atomic masses and why it's not a whole number, the atomic mass of an element is calculated using the... Well, when you look at these problems, I want you to take your time and look at all 4 choices. They're using atomic number and ratios of isotope, atomic number and half-life, masses and ratios of isotopes, masses and half-lives. So they obviously have these 4 choices, and we can eliminate 2 of them if you know one of the 2 parts. Okay, so if you can remember that mass is, of course, based on their masses, hopefully you're automatically going to get rid of the atomic number ones. That leaves us with ratios of isotopes or half-lives. Right now it's pretty simple because we haven't talked about half-lives yet, so half-lives must be wrong. And it's a little tricky because they use the term isotope here, but look for other keywords. So it's not going to be half-lives, masses, and the ratios. You kind of have to memorize that. That's going to be your answer. This is typically how they're going to ask you about the atomic masses in a multiple choice question. They have asked you to actually calculate the weighted average in a short answer, so this was from a final exam. So the element krypton consists primarily of 3 isotopes: krypton 84, krypton 83, and krypton 81. Now you have to know that these are the masses. Those little numbers at the top are the masses. The composition of a given sample of krypton is 70% krypton 84, 15% krypton 83, and 15% krypton 81. Find the average atomic mass of the sample. Sometimes they'll ask you to just set up the numerical setup. We're actually going to solve for it. So what I would do is say, well, krypton 84, 70%, so 0.7, has a mass of 84. And for krypton 83, 15%, or 0.15, has a mass of 83. And for krypton 81, it is also 15%, so 0.15, has a mass of 81. So I need to multiply all of those things out. And then to finish it, of course, don't stop there. Make sure you finish it by adding them together. We're just going to round it to 83.4. Leave the one decimal. AMUs is the proper unit here, or just U they're using now. You can also use. And that's it. It's as simple as that. I know you've done weighted averages in math, probably in algebra. So again, freshman year, you might not remember it. Find it somewhere in the back part of your brain. Your brain remembers how to do it. Now you can apply it to your chemistry. And that's it for Lecture A.